Yeah, my name is Künneth. I'm a professor at UBT since 2023. Before that, I was in the United States for a long time, and today I want to talk about, the topic of polymer informatics, which is essentially the connection between informatics or data science methods and polymer science, but you can extend this also to materials informatics, which would be then the connection between material science and data science. The reason why we are doing this, or why I'm trying to do this with my research group, is because we want to accelerate things. We want to make things faster. We want to, develop new materials faster. We want to come up or design polymers faster with specific functions that, we require for some specific products. I like to start with this image here, where you can see a haystack here. And you can see needles in that haystack, and you can see also like a magnet and a person. And you might see that this is AI generated. That was a large language model around 2023, so pretty bad quality, as you can see. But still, we kind of understand what is on the picture. If you put some words or keywords here, then we could say this is somehow our challenge that we all face. So we want to maybe discover or find like a specific new material, but the configuration of space is just extremely large and extremely complex. So we are looking for a needle in a haystack. And this is a tedious and, costly, whatever process for company and researchers. And that's where AI or generative AI comes in as a magnet. So it helps us to find the needles in the haystack much, much faster. And then there's, of course, us. We are kind of like controlling this AI to some extent, right, what it does. And then I ask a large language model to come up with another metaphor here, like how, this challenge looks. And it came up with this image. You see it has much more details. It's, I think, produced last year by Nano Banana Pro, by the Google picture model. And I asked it to envision like this haystack. And it came up with this hyperdimensional haystack. So the challenge is very, very complex. So it's really a hyperdimensional challenge that we are facing. And we try to, not just find needles here. We also maybe try to find other, metal parts here. And in this image, you see this haystack here, which has all these metal parts in it. And now, next challenge that arrives is that some of these metal parts might be not magnetic. So you can't really, collect them or find them with a magnet. And this is where a new tool arises at the horizon of AI, which is agents. They are agents. So AI agents are some autonomous systems that, can do or execute tasks for us and use one or multiple tools to execute tasks that require one or multiple steps. So here in this metaphor, it would be like the collection, but also the sorting of some metal pieces here. Of course, our challenge is not the haystack itself. And I phrase my challenge as what I call the materials universe, or the polymer material universe. And you can envision this universe as a very, very large configuration of space that contains all the polymers you can think of. And only a very small subset, like some small planets or small solar systems in this material universe, have been synthesized so far. So it's very, very large. There are many, many more materials in that universe that might be interesting. If you want to zoom into this materials universe, then you can define your own galaxies. Here, some material-specific galaxies, like the polymer galaxy, that contain specific solar systems, and these solar systems might contain specific planets. And on these specific, maybe every one of us, we work on our own material system on our own planet, and we search on this planet for the perfect, needle in a haystack, for the perfect solution. There might be there's of course also molecule galaxies where you maybe discover new drugs. There's metals, there's ceramics, and so on. So today I want to focus on this polymer galaxy. So I told you it's a large configuration of space, and if you would want to somehow envision this universe or visualize this universe, then you could say that it contains these things. First of all, we have some different elements, like in the polymer structures. We have different motifs. We have different polymer types. We have homopolymers. We have copolymers. We have polymer blends, and, you know, the copolymer and polymer or the copolymers, they can be connected in a different way. Here you see like a homopolymer contains like, you know, some repeat units, and a copolymer contains like 2 types or more types of repeat units that are, you know, connected, for example, in a random fashion, alternating fashion, block fashion, or crafting fashion, whatsoever. Like all these configurations that you have are like in this polymer universe. And if you want to find the right solution with the right property, you need to somehow access or like find the right solution for your property. There's also processing and shape modifiers, you know, molecular weight or molar mass distribution here, which you can see on the right, which is a very specific target for polymers. Like if you have bulk polymers, this describes the chain distribution in this bulk polymers, like how many chains of this length are in this bulk piece of polymer, for example. And on average, you get like such a distribution. You have also additives, like if you look at real-world examples of polymers, like these additives, they modify the properties of the polymers. For example, they change the mechanical properties of it, or they make it more resistant to sunlight. Like all these things are like today done by like many additives that we add to these polymers. We have process conditions, post-treatments, and also forms matter. Like if you have a sheet, a polymer sheet, or polymer film, or polymer fiber, or whatsoever. So they all like somehow changed it. So you can see that this configuration of space is just immense. It's just super large. So you have no chance at all to just search it by experiments because we don't have time. So we need to accelerate it. And if you now want like another view in this polymer universe, that you can use a method that, you know, here is a pretty old plot, but it's a principal component analysis plot where you can see here some dots with different colors, and each of the dots is an experimental TG value of a polymer. So TG is the class transition temperature of a polymer, which is a very specific temperature that we measure, which is a very engineering property. So if you want to find polymers and use them for specific purpose, then one of the first goals is to find polymers with the right TG value. So here you see many data points of experimental polymers, and you see they have a color. And the light blue color shows like polymers with low TG values. And the purple one shows polymers with high TG values. And now the interesting fact here at this, you know, visualization of this universe is that there's a gradient somehow visible, right? Top right corner, you see purple. Bottom left corner, you see light blue. So the PCA plot actually has meaning. It has somehow found ways of organizing our data points in a way, in a meaningful or chemical meaningful way. And the same we can also do, like if we visualize polymers that have amides, imides, ketones, or acrylates, or other structures containing, then we get some kind of like slices in this universe, which you can envision at the solar system. So this is actually a very beautiful way of showing like these kind of like universes. Okay, there has to be the explorer of the universe, and that's my research group, as you can imagine. And I'm, you know, still growing. I said I started 2023, and now it's 2026, and the last picture is from 2025. So we are evolving essentially, and we all have these cool hoverboards that we use to fly around the universe and explore the universe. Yeah, eventually, polymer informatics can be maybe prescribed like you see on this slide. So we have this large polymer galaxy on the left, which is very large. So it has Google 10 to the 100. That's the word that says 10 to the 100, or, you know, more than Google, or infinite materials in it, because there's so many combinations. And on the right side, you have like a specific product or material you are trying to use for like a specific application. And in this case, I have the vision of, you know, creating a cradle-to-cradle bioplastic ball. So this is a plastic ball which is not made from PET like we use it every day. It's made from a plastic that can be created with bioorganisms and degraded also with bioorganisms. So once you empty it, you just throw it in your compost, and within 30 to 60 days, it has become soil, as you can see here. So now, usually we have, you know, these, you know, slow experimental approaches to finding such a material. And this is where my group comes in. So we use machine learning, generative, and agentic AI. and also to some extent like more traditional methods like DFT and MD, but mostly for producing data to train machine learning models, to solve this problem in a forward and an inverse way. So first of all, we do like materials, so polymer property prediction models a lot. So we have as an input a chemical structure or like a material structure, and as an output, we get like TG or any other property that we want to predict. Many other models we train, they do, fulfill the inverse design criteria. So we train machine learning models that you can give specifications of the material we want, like degrade within 60 days. And the machine learning model will come up with a chemical structure, a new polymer for you that you should use for that. We also deal with material synthesis route predictions. Like now, you have proposed maybe a new chemical structure, then people would also want to know how to synthesize, how to make, how to produce, how to process this material to give it this property. And of course, we deal a lot with data. And we deal with data collection, we deal with data curation, we deal with data storage. So all this comes with this field, of course. Now I have a small demo that I need to play on my laptop, I believe. So this is a project I've worked on. It was one of my postdoc projects, actually, and it's called Polymer Genome. So think about this project. You can think of like humans have genomes that somehow give us the traits that we have. In a similar way, you can think that materials also have a genome that give the specific properties to these materials. That's why it's called polymer genome. And it works like this. So you have a website, and then you put in one of these smile strings that you can see here, which is essentially a line notation for a polymer. So this would be polyethylene. That's PP, polypropylene. And then you can put other polymers here. And once you can also draw it like in a chemical drawing, but you can also just write like this. And then you hit predict properties on the right. And then within seconds, or like less than a second, you get all the properties of this material. So you get electronic properties, you get dielectric properties, you get thermal properties, you get physical thermodynamic properties, you get mechanical properties, you get permeabilities, and you get solubility properties. So you really get and this is a bit of an old version of this website, so now it's even more. So many people have worked on this for years. You get ultra fast polymer property prediction, which is, you can see, extremely helpful for people in the lab because they don't need to synthesize it. So they just put the structure, they get the properties, and from this they can decide if they go to synthesis or not. So it's really a tool for accelerating things. All right, that was an introduction, and I think I have roughly half an hour left, and I want to show you some specific projects we are working on in my research group. And the first one I want to mention is by Subhash, and he works on accelerating battery science with machine learning. So what he does is that he search in this large material universe here on the left in leopard speed using machine learning, generative, and agentic AI to design or find new organic-based sustainable batteries with high performance, with high KPIs. So performance of batteries are measured in cycle stability, specific capacity over time, stays constant, voltage, and so on. We want to have the battery to be very to contain lots of charge, but be as light as possible, for example, like all these things. And the vision behind this is to create an AI agent for designing batteries. So here on the left, you can see a battery stack. So we would have a positive electrode, we have interface, we have a separator, we might have a separate, we have an electrolyte, we have another interface to the negative electrode, and we also have two current collectors. So it's just a typical battery stack that we use. And then you have your charged ion, which is your lithium ion that moves either to the top or the bottom, depending on if you charge or discharge or use the battery. And on the outside, you have a wire where the electrons essentially flow to compensate for the lithium that moves in the battery. So now you would know or see that, okay, the energy to move that charge carrier, lithium ion here, from positive to negative or the opposite way is somehow proportional to the battery voltage. So you can, and then this would be a task for our AI battery agent that we're developing. So the task would be to maximize the battery voltage. And we also kind of plug in here a solar system of our choice. For example, we can tell these AI agents to only search in, the sustainable polymer universe, or sustainable organic solar system. And then this AI agent comes up with some example prediction of materials that we should use in a new battery that gives you like excellent voltage or excellent KPIs that you actually require the model to have, or it maximizes this. So from here, you can go in the lab and then create this battery. The agent is, and this is just, I mentioned this here because it's a question that comes up. Of course, the agent is somehow aware of all the interfaces or the interactions that go in this, or that runs in the battery by learning this from data. Okay, how did we do that? We started with data collection. This is one thing we also do a lot in my group, so we somehow need to get data. And you all know I don't have to tell this crowd here, but data, especially experimental data, and if you look in the 70s, 80s or whatever, it's not accessible. It's not you download the Excel file or CSV file and you have it. So you need to collect it manually, you need to create it manually. We're also developing large language models like agent for that extract material records automatically for us from the literature that work to some extent, but they cannot completely mitigate the work of currently of humans. We still need some humans in the loop to do creation and all that. So we collected 771 data points for voltage-specific capacities of polymers and molecules from the literature. That was the first step. Then we trained a machine learning model, and we usually opt for data fusion models. These are specific machine learning type that can multitask and multi-fidelity learning. It's a deep learning neural network, and we also opted for virtual screening to do the inverse design process. We are then, here on the left bottom, you can see in this picture essentially the data set that we have collected here. You see it's for different charge carriers. It has redox active and redox non-active materials in it. And here, these two plots, they show you the parity plots of the model performance, which have on the y-axis the predicted voltage and on the x-axis the targeted voltage. So if someone doesn't know these plots, if all points align on the dashed line, then you would have the perfect prediction of your model. We call this parity plots. And then we can also measure this in numbers, in metric. And here you use the R2 value, which is defined between -infinity and 1. So 0.89 is actually a pretty good and decent value for the voltage, and 0.78 is for capacity. So we were pretty, there was a good model, training worked well and everything. So once we had set up this, we did the inverse design steps. So in the inverse design step, we designed or thought about like large library or large planets that we want to search for like new combinations or materials that we can use in batteries. And we, opted for like designing a high-performing planet, a stable and a biodegradable planet. And then we used the machine learning model to search for, or like to predict all the here a voltage and specific capacity in these on these planets. And if you probably know these banana plots here, so you have seen these for other things, but you have here the voltage over the specific capacity, and if you multiply them together, you get some from the energy density of a battery, which is then essentially measured like watts hours per kg. So it's like energy per weight. This is a very important KPI measurement here. And now you see we have also put experimental data points here that are for currently available combinations and materials, which are the blue ones here. But you also see that there's many new data points, and the color just shows the density of the data points here that are actually more or like higher than like the so far discovered experimental combinations for these batteries. So essentially, when the banana unbends here at these points, like you get the high energy density materials that we're looking for. So here we discovered new materials, and they can now, the design of these materials can now pass on to experimentalists, and they can produce these new organic materials and add them to batteries. Yeah, that is just the beginning of the story. So as I said in the beginning, we are currently working on the second version of that. That's also all cycle independent. So batteries have the property of we want to last them for some time. And the time measurement here is not, the daytime or like the time we live So it's the time of cycles. So you want your phone to be charged at least, I don't know, in its lifetime of the phone, maybe every day. So you want to last it for whatever, 3 years. So you want 1,900 to 1,000 cycles at least, probably more. And you want to keep the KPIs, these properties, to stay the same. So the next version of that will then also take this one into account. And we this time we still use data fusion machine learning models that are able to learn from inherent and sparse materials data sets that are usually prevalent in material science. We combine them with deep nets that are learning method that can learn complex and nonlinear operators from functions, and in this case, it would be the operator between the capacity and the cycle function, which is a very interesting approach. It's a bit of the opposite of pins, if someone knows pins, but pins have it's very difficult to train physical informed neural networks, which are pins. So deep nets are like a bit of a new way of doing that. We directly learn the operator here. Yeah, then the second project is then also of what Ahmed mentioned, of one of these CRCs, which is the microplastics CRC, and it is by Sunir and Henry, and it's about the toxicity prediction of polymers. So what we do here is that we essentially want to somehow come up with polymers, or we want to classify and predict the toxicity of polymers. And this is not just you're toxic or non-toxic. I mean, on the first case, yes, but toxicity has you have a finer resolution here of categories, something like carcinogenicity or mutagenicity or specific target organ toxicity or aquatic toxicity. So these are all categories defined by some organizations, and you want to test if these polymers have these properties, because if you think about microplastic that is somehow transported to our environment, and it accumulates in our bodies, but also it accumulates in animals, then it would be interesting to know if it has some toxic effects or not. And also you can see that these microplastic particles, they become smaller and smaller and smaller, and then they might even change their toxicity over time. So this is we want to tackle that here with machine learning. And it's a bit in the beginning, this project, but what we did here is that we first started, with a molecule toxicity data set, which is called TOX21. Some of you might have heard about it. It's a data set of, I think, 10,000 small molecules, and tells you if this molecule is carcinogenic, mutagenic, or has any other toxicity, which is pretty interesting. And then we first trained classification machine learning model, pretty simple with this, and we got, as you see here on the right, if you're not familiar with this plot here, it's ROC plot, and essentially what we want to have is that these lines to be as much as possible in this left corner. So if you were to integrate under this curve, it's a 1 by 1 plot, then you get 1 as an area. So here we also compute these values. Here we have the area under the curve of 0.8 or 0.7 roughly, which is a pretty decent model, and shows that the machine learning model has worked. That was on molecules, but as I told, we want to do this for polymers. So what we do now is we do a strategy called the machine learning transfer learning. So as you learn tennis, it will be easier for you to learn badminton afterwards. What is the reason for that? Because you learn how to use a racket in tennis. And the same idea we use also in machine learning models. If we train machine learning models in a specific domain, the molecule domain, then they will have some knowledge about polymers, right? Because they're somehow similar, right? We can do the same, domain example for many, many things, and this really works. So here we actually then, in a second step, we started with the pre-trained molecule machine learning model, and then applied a couple of transfer learning methods, here fine-tuning, zero-shot, and few-shot learning to it. And for this, we collected a very small 55 data point data set for polymer toxicity that we can use. So it's much, much smaller than the 10,000. So we take the pre-trained molecule model, and then we fine-tune or few-shot learn it on the small data set. And we did a couple of methods. We did like zero-shot learning, where we essentially just use the molecule model to do predictions in the polymer space. We did few-shot learning, and we did also like transfer learning in 2 different ways, like fine-tuning in 2 different ways. So either in one case we just have unfixed all the the entire network. In another stages, we started to fix some of the layers and then just fine-tune like other layers in that new network. And the results are actually pretty good. So we, in comparison to our baseline, the polymer-only baseline, like training a model with this data set, which would be the baseline, we could improve by really a lot. So this is, the AUC, the area under curve, went from 0.47 to 0.92. So this shows, at least in this example, that we can really learn between two different domains, and the poly domain really suffers from not having any data availability in comparison to maybe the molecule data, the molecule world where we have more data. So first, it's a really legit approach to start with molecule data sets and then transfer them into the polymer domain. And it works kind of nice for toxicity, so we expect it also to work nice for other properties. All right, the second, a bit more computer sciencey, third, bit more computer sciencey topic I want to talk is by Ibrahim. And Ibrahim is essentially or was working on finished that on a topology-aware structure graph. It's a graph neural network encoding that improves the performance on polymer property prediction. So you see this, I already put the archive label here, but the archive should be published, I think, yesterday of this paper, but it's not available yet. So you probably all know, I think it takes 1 or 2 days to be available. So I couldn't do the link. He is also in my ERC starting grant project, GenPI, which is about generative polymer informatics. So the idea here is a bit that we predict molar mass dependent properties of polymers. So molar mass is this distribution, which I showed you in the beginning, of chain lengths or different chain lengths in your polymer. And you can see that experimentally, you can control the change length distribution, the molar mass distribution, and by this also change all the properties that are derived from that. And TG is one which is very sensitive to this molar mass distribution. So if you make it narrow or you shift the entire distribution, then you would also change these properties. And one particular industry that is interested is the rubber industry, because they are use polymers very much like, or for them TG is very important. That's why I put like this rubber picture here, or like the tire picture here. There's also many other properties that somehow depend on the molar mass distribution, like mechanical properties of polymers and so on. So it's like a bit like the, in inorganic system, or in metals, you could think about the grain size distribution or something that also like, changes the mechanical property of like something like really by a lot. So the same happens here in polymers. And again, we started with a data set. This time we collected 381 experimental homo and copolymer TG data points with molar mass dependent. That was actually quite difficult because, molar mass dependence or molar mass distribution is not something you naturally find in literature. So you would kind of like dig deeper or go into like very specific literature to give this to get this data set. And then we came up with a data set of, here you see the distribution. It's just a frequency plot of this data sets in homo and copolymers divided. And you see it's somehow a bit Gaussian distributed, about 350, 360, 370, whatever. So, and there's, I think it was more copolymers than homopolymers, or roughly the same in the data set, but it looks kind of like a distribution that is okay. And on the right side, you see the molar mass coverage, which is important because if you want to train models that are sensitive to molar mass changes, then we also need to make sure of the diversity of our data sets. And this is one thing also that I always tell people that want to work on machine learning, material science. We need quality of our data, which is important, but we need also diversity. Otherwise, our models are not very useful at the end of the day. They maybe get good, we may get an extremely well and good prediction, but we also need the diversity. And the diversity, very often you don't get from your own experiment. You need to go into literature to find a diverse set of data set. That makes your models at the end of the day in material science and materials informatics actually useful. Yeah, the second thing we did, and this has kind of been done before, like to take and you can think of any kind of molecule or any kind of polymer and convert it into a graph, right? So the atoms are naturally converted to nodes or vertices. That's another word. And the bonds they are somehow naturally converted into edges or connection between the nodes. That would be a very natural connection. So if you have a small molecule that has, I don't know, like 500 atoms, well, that's not small, like 10 atoms, and you have then 10 nodes and like all the bonds that you expect. You just naturally convert this into a graph that you can directly use in graph neural networks. Here in polymers, this is a bit different, right? In polymers, we have repeat units. So we have, this one is polyethylene. So it has 2 carbons, and the n means it's repeated n times. And for different n's, you would then build up this molar mass distribution. So most people, they just went for the approach of looking at the repeat unit only. So if you only look at the repeat unit, of course, you have all these statistic effects that you have in a polymer chain that will, change for different chain lengths, or it has different changes, which you can't really have this in a model, or you need to somehow hack into the model to give this as a global property. So here we opted actually for another approach. We really fully encoded the polymer graph. So we did really large graphs. So we take the entire length of the graph and of the polymer and converted this into a graph. The way we did this is that we have the molar mass distribution of the polymer, and then we designed 4 cups, and in each of these cups we randomly draw a specific distribution or specific chain length, or we draw chain length from the molar mass distribution, and then construct the entire graph. So these are much, much longer. So here we really look at the full graph instead of the small graph, which then, of course, has the advantage that you can model all these statistic effects in polymers, and also, get something like a molar mass dependence, TG dependence or property dependence of the molar mass distribution. Yeah, and this also turned out to be very good. So we got a very good prediction performance with 24 Kelvin. Resolution, meaning that it's our RMSE value. RMSE is like another metric. We use a lot of machine learning, which kind of like tells us it's the root mean squared error, which tells us a bit like, how's the, accuracy. And it has a unit, so it has the unit of the property that you predict. So we predict TG, which is Kelvin in this case. It's though a nonlinear measure because it's squared and then a root, so it's not directly like the accuracy or something. But you can say that, okay, we can predict, this within 24 Kelvin or whatever. We then plotted these TG over M prediction sweeps that you can see here on the right, meaning that because we now have all these dependencies, we can just produce all the sweeps. So we can take a polymer, we can sweep essentially over the MW, which is one of these properties that describes this distribution, NMN, and also the dispersity, which is just the ratio. It's one over the other. So we can just sweep all these values and then plot it, which is very nice again for polymer scientists, because for them it's very important, because they maybe want to adjust the TG value to be exactly this value. So we tell them you need this dispersity, and you need maybe this MW, but there's maybe also other possibilities for how to get the exact same TG with another set of MW and MD. So this is all these sweeps, they have all this information. And also what we can see here, that there's some kind of like chemical physical laws, that one is called the Fourier-Fox equation, that somehow describes the natural behavior of this, and it follows that physical chemical intuition like these sweeps. So it's another kind of like also validation of our model here. All right, so how much time? 10 minutes left. Maybe the last topic, and I want to talk about it. It's a bit older, but I think it's still pretty cool, and we use it in most of our works. It's called Polybird. And Polybird is this here on the right. It was also generated by AI, as you can see, in very early days. So if I ask like AI how Polybird looks, and Polybird is interesting in the sense of that it's a language model that speaks polymer chemical language. So like you talking to ChatGPT, to Gemini, to Claude today, hey, I don't know, find a good recipe for the ingredients I have in my fridge, or any scientific questions. Like this model is not trained on the natural language. It's not trained on English, it's not trained on German, it's trained on a chemical language. So as a model that has been trained on a natural language become a linguist, this model becomes a chemist, because it's been trained on a chemical language. So if you would train it on your own language, then it becomes like a linguist in this language, and this language is designed to tell you about chemistry, then it becomes a chemist. That's the idea behind that. So here, this language is the PSMICE or SMICE language, which is a specific language. You've seen this in polymer genome before, but it's a language that essentially is a line notation for the chemical drawings. And these stars, they just show the repeat unit of the polymer. But it also works for molecules. And, it has been trained essentially like you would also train a natural language model by looking at language. So we have trained it by looking at chemistry examples. So I've created like a data set of 100 million hypothetical polymers, and then Polybird has looked at all these examples 100 million times, and by this has learned chemistry. So it knows that, there's some certain things, chemical valid or invalid structures in chemistry. So we can call it the grammar or the syntax of this polymer language, and has learned about this, right? And by just, learning this space, this language, and can create meaningful latent space representation of this language, which are very, very helpful later. The inside of it is something that you can see in light. So if you butcher it and open Polybird, if you want to, then this is kind of the pipeline it has in the inside. So there's some pre-processing step where we need to take care of canonicalization of these strings. It's several reasons for that. We need to somehow tokenize it. That's just for the upcoming large language model. We need to mask it to create our self-supervision learning problem, because if you run language, we have an unsupervised problem, an unsupervised machine learning problem. So we somehow need to create one, and the way we do this is by removing information and asking the model to come up with the missing piece, with the missing information. Then there's a deburter layer with transformer encoders, and then at the end you see the missing token has been found by Polybird. And doing this 100 million times with the language, you train these models to become chemists. If you have more interest here, please ask me later. I'm happy to also discuss more on this. So as said, it speaks polymer language. It's somehow, it was trained on lots of data and has learned chemistry by looking at chemistry. So like, training this model. And it's very, very fast. That's here one of the key things. We have done such things in the past, like in a traditional handcrafted way. And, this one is just 2 orders of magnitude time. So it's, I always tell people about acceleration. So this is really 2 orders of magnitude is something. So here, an example, we can do 13 hours, we can screen 100 million polymers. And if you think about with 30 properties, right? So if you think about the large universes that we actually act in, then this is very, very helpful to do find and discover new materials. Yeah, it's just traditional versus the Polybird pipeline. Traditionally we would start with some kind of a data set. We go through some handcrafted fingerprinting process and then do some prediction. And in this way we go to Polybird, which then on leopard speed lets us allow to predict properties. And you see here that this is the traditional approach here. And then we have quite some acceleration here. The y and the x-axis are on log scale of Polybird. Yeah, and then there was a wedding with these data fusion machine learning models that they fell in love. And by combining these 2 systems, and that's what we do a lot in our research, we can essentially create these really cool pipelines of finding new candidates for experimental people in the lab to synthesize them. By essentially asking a question to Polybird, we can somehow plug in or like decide on our solar system, like where it should search. And then we also need some kind of a prediction hat that is designed specifically to this question, and then it will come up with some new polymer or like also drug candidates that can be then given to experimental collaborators. I'm gonna just skip this and go straight to the takeaway. My second, this is my last slide for today. So I just want to really give a very brief and quick summary. So I think predictive and generative and now agentic AI, which is really cool. So there's lots of progress this year in agentic AI systems, and I'm really excited about this to also use this in the material science space because it will help us a lot. It accelerates, but also improves somehow, right? It makes things better, not just faster, also better. Material science and engineering, and AI can quickly search this large materials universe for new materials and processes. And then on the data side, we all know that data is very important. So at least for me, as a person who really uses lots of machine learning data, is really crucial and important. And there's not enough data. We need more because data quantities at the same time also quality, right? So if we have lots of data, then we solve also lots of quality problems. And with this, I just want to maybe quickly mention, or you can see my funding sources. There's European Union, the Horizon 2020 program, High-Tech Agenda, the BEAM FTR, the DFG, the ERC, Humboldt, and the BIBAT, the Bavarian Battery Center in Bayreuth. And then thank you for your attention.